December 19th, 3I Atlas makes its approach, an interstellar object that has accelerated, shifted course, and generated signal patterns nothing in nature should produce. At this point, the question isn't whether it's unusual, it's why it behaves as if it has purpose. And with every subtle velocity change, the artificial origin hypothesis moves closer to the center of the discussion. In this episode, we cut straight into the evidence, what scientists actually know, what remains uncertain, and why quiet government protocols are already unfolding behind the scenes. If you find work like this valuable, don't forget to like and subscribe. It helps us keep delivering clear, science-driven analysis. Now, let's begin. You could say that the countdown has already begun, not to an impact and not to a clear disaster, but to a quieter kind of turning point. It is the moment when many people might look up and notice that the sky is not exactly the same as they thought. The object at the center of this story is called 3I Atlas, officially labeled as a comet, and it is expected to make its closest approach to Earth on December the 19th, 2025. Some independent observers think that, under certain conditions, it might become bright enough to be seen without a telescope. Others are more cautious. Either way, it is an interstellar visitor, an object from another stellar system passing through our neighborhood. On most calendars, December 19th looks like an ordinary Friday near the end of the year. For some scientists and planners, it is also a date to watch closely. 3I Atlas is projected to be about 1.8 astronomical units from Earth at that time, which is roughly 270 million kilometers. That is a huge distance in everyday terms. But in astronomy, visibility is less about distance and more about how much light an object gives off or reflects. A dim object nearby can be harder to see than a bright object far away. For comets, that brightness is controlled by their size, their surface, and especially by how volatile material inside them responds to the sun's heat. The standard view in the scientific community is fairly modest. Based on current models, 3I Atlas should reach an apparent magnitude of about 11 to 12 at closest approach. On the magnitude scale, smaller numbers mean brighter objects. Stars you can see easily by eye under dark skies have magnitudes of about 6 or brighter. A magnitude of 11 or 12 is far too faint for unaided human vision. It belongs in the domain of telescopes and long exposures, not casual stargazing. So why is there talk about possible naked eye visibility at all? That comes from two main sources: the nature of comets themselves and a handful of unusual measurements. Comets are difficult to predict because they are not solid, inactive rocks. They are mixtures of ice, dust, and gas that can change quickly as they warm up. Interstellar comets, which formed around other stars in colder and more distant regions, may be even more unpredictable. Their chemistry is not guaranteed to match what we are used to in our own solar system. In the case of 3I Atlas, the James Webb Space Telescope has already given us a clue that this object is different. When it observed the comet in infrared light, it found that the coma, the fuzzy cloud of gas and dust around the nucleus, is dominated by carbon dioxide. Many comets in our solar system have comas dominated by water vapor with other gases mixed in. Here, water appears as only a trace component, along with carbon monoxide, dust, and other ices. A carbon dioxide-rich coma suggests that 3I Atlas formed in a much colder region, where carbon dioxide could freeze in large amounts. Perhaps far from its original star, carbon dioxide ice turns directly into gas at lower temperatures than water ice. This process, called sublimation, can start while water ice is still stable. That means that as 3I Atlas gets closer to our Sun, pockets of carbon dioxide can suddenly turn to gas and escape, carrying dust with them. These outgassing events can cause rapid and uneven changes in brightness. For a while, the comet might look fairly steady, and then, over a short time, it could become several times brighter as new jets switch on or existing vents open wider. This is one reason why some observers have been watching its light very closely. Amateur astronomers with good equipment have reported what they describe as flares or pulses in the brightness of 3I Atlas. They share plots of its light over time, called light curves, and some of these plots seem to show short-lived bursts rather than a smooth rise or fall. A few observers think they see a rough repeating pattern, which could mean that the nucleus is rotating and that active jets on its surface are sweeping in and out of view. In that picture, the comet acts a bit like a slow lighthouse, with different bright regions coming into view as it turns. However, these claims are difficult to confirm. Many of the measurements are near the limit of what small telescopes and cameras can reliably detect. At those limits, many sources of noise can affect the data. Turbulence in Earth's atmosphere, small tracking errors, differences between camera systems, and the faint background glow of the sky itself. All of these can introduce fake signals that look like real changes. Even careful observers have to correct for these effects, and the corrections are not always perfect. As a result, some scientists remain skeptical about reports of strong flares until they can be confirmed with larger instruments. This debate over brightness has led some people to talk about a data war. On one side are many amateurs and a few smaller observatories that report irregular pulses in the light curve of 3I Atlas. On the other side are major, ground-based, and space-based telescopes, whose data look more stable and easier to fit with standard models. The numbers themselves, measurements of how much light reaches the detector, are neutral. The disagreement arises when different teams try to filter, calibrate, and interpret those numbers. To understand what is at stake, it helps to look more closely at what a light curve is and why it matters. A light curve is a graph of brightness versus time. For comets, light curves tell us how the overall activity of the object changes. A smooth increase in brightness as it approaches the Sun can be explained by steady warming and increased outgassing. Sudden jumps may signal that a new crack has opened in the surface, releasing fresh gas and dust. Repeating patterns can hint at rotation periods and the distribution of active regions. From these patterns, scientists can infer things about the comet's spin, its shape, and the structure of its near-surface layers. For an interstellar comet like 3I Atlas, this information is especially valuable because we have almost no prior examples. Before this, only a very small number of interstellar objects have been identified, and only one or two have been studied in comparable detail. That tiny sample size means that every new measurement carries extra weight. If the light curve of 3I Atlas shows unusual behavior, it could mean that interstellar comets are different in important ways from the ones that formed with our Sunday. Or it might simply mean that this particular object has an unusual history. From the point of view of large observatories, the light curve of 3I Atlas so far looks fairly ordinary for a comet in its situation. When they plot brightness versus time, they see variation, but it falls within the range that can be explained by standard models. In those models, solar heating drives the release of gas and dust, which forms a coma and sometimes a tail. The coma scatters sunlight, and as the total amount of gas and dust changes, so does the brightness we see. Small bumps and dips in the curve are expected. They do not automatically imply something exotic. This more conservative picture does not deny that 3I Atlas is interesting. Its origin outside the solar system and its carbon dioxide-rich coma already make it a rare and valuable object for study. It simply suggests that, up to now, the data do not clearly force us to abandon the usual physics of comets. From this viewpoint, reports of strong flares and dramatic pulses may be more about the limits of small instruments and the human tendency to notice patterns in noisy data than about the true behavior of the comet. Still, even within this conservative framework, there is room for uncertainty. Because 3I Atlas is the kind of object we have almost never seen before, scientists know that their models may be incomplete. They must treat their interpretations as provisional, open to revision if more precise measurements show something new. This is part of why professionals continue to observe the comet closely as December 19th approaches. They are not expecting an impact, but they are aware that an interstellar comet passing through the inner solar system is a rare chance to test their understanding. Outside the technical discussions, there is also the human response to consider, even if we describe it in simple terms. The idea that matter from another stellar system can pass through our skies, perhaps bright enough for people to notice it without any device, is powerful. It makes clear that our solar system is not isolated. It is part of a larger galactic environment where objects can travel between stars over very long timescales. Even if 3I Atlas remains a faint smudge in telescope images, this realization alone can change how some people think about their place in the universe. In this mix of precise measurements, uncertain models, and human curiosity, the disagreement over the light curve of 3I Atlas becomes more than a narrow technical issue. It shapes how confidently scientists can speak about what the comet will do next, how visible it might become, and what lessons we can draw from it. For now, the best summary from major facilities is cautious. Their instruments show a comet whose brightness can be explained by known processes: solar heating, outgassing, and scattering of light in the coma. There is variation, but nothing that clearly demands a new theory or points to an extraordinary anomaly. The disagreement between different groups of observers does not automatically mean that one side is right and the other wrong. In many cases, they are simply measuring different aspects of 3I Atlas at different times, using instruments with different strengths, sensitivities, and sources of noise. When you combine that with a faint, distant, changing target, it is not surprising that the resulting pictures do not perfectly line up. One idea that has attracted attention in some independent circles is what they call a pulse cycle. A few observers claim that 3I Atlas brightens and dims on a schedule of roughly 11 to 16 hours. They argue that this behavior seems too regular to be pure randomness, yet not regular enough to fit a simple, single rotation period. In online astronomy communities, people have built long spreadsheets of brightness measurements, comparing light curves from various nights, trying to see whether a repeating pattern really stands out from the noise. Their discussions explore several possible natural explanations. One suggestion is that multiple active regions on a rotating nucleus are turning into and out of sunlight, so that different jets dominate at different times. Another is that tidal stresses or internal cracking could cause periodic bursts of gas release. A third line of thought is that the pattern does not sit comfortably within the usual box of comet physics at all. It is important to note that none of these claims about a pulse cycle have been confirmed in peer-reviewed journals. They have not been endorsed by the major institutions, whose job is to track and characterize such objects. That lack of formal confirmation is precisely what makes the situation feel uneasy for some people. There is just enough structure in the amateur data to provoke questions, but not enough solid evidence to settle them. This so-called data war matters because it shapes the story people tell about 3I Atlas. If you place your trust mainly in large, institutional measurements. The comet looks like a normal, if interesting, interstellar visitor. It follows expected patterns, shows activity driven by solar heating, and is noteworthy mostly because it comes from beyond our solar system. If, instead, you give more weight to the amateur observations, you may end up with a picture of an object showing structured, rhythmic variations that hint at internal processes we do not yet understand, or at least have not often seen. In a world of instant communication, both versions spread at the same time. Careful, conservative statements from observatories appear next to animated plots from backyard telescopes. Speculation can travel as fast as, or faster than, verification. For many people watching from the outside, it becomes difficult to know which story reflects reality and which is a product of limited data and human pattern recognition. There are reasonable questions about why agencies might seem to downplay reports of unusual brightness patterns. The generous reading is that they are simply being scientifically cautious. They want to avoid endorsing claims until the evidence passes strict tests for reliability and repeatability. That is a core principle of science. The less generous reading is that they are managing public perception, choosing their words to avoid alarmist headlines or distractions from other missions that also need attention and funding. It helps to remember the environment in which agencies like NASA operate. They are responsible for many projects at once, from planetary probes and space telescopes to climate studies and human spaceflight. Their work is closely tied to budgets approved in political systems that do not always reward nuance. If 3I Atlas eventually behaves like a fairly ordinary comet, any early talk of strange patterns or possible anomalies could be used to claim that scientists exaggerated. That would harm credibility. From that perspective, it feels safer to understate than to risk overstatement, safer to wait for high confidence than to speculate publicly and later walk it back. At the same time, it is worth considering what it would mean if some of the independent observers are indeed capturing real physical behavior. If those brightness spikes are genuine, one straightforward explanation is that they represent outgassing events. In that scenario, jets of sublimating carbon dioxide erupt from pockets beneath the surface as they are warmed by sunlight. If there really is a rough periodicity, it could reflect the rotation of an irregular nucleus, with active regions that come into view on a repeating schedule. These would all be natural, if scientifically exciting, findings. They would teach us more about the internal structure of interstellar comets, about how volatile ices behave after spending long spans of time in deep cold between stars, and about how objects formed in distant planetary systems differ from the comets we know. There is also a more speculative set of ideas that some people raise in less formal spaces. In these scenarios, brightness variations might be linked to changes in surface properties as old, radiation-damaged crust breaks apart and fresher material is exposed. Others go further and ask whether some outgassing could be controlled rather than random, with patterns that look like deliberate timing. At the very outer edge of speculation, a few voices talk about shifts in the object's energy state or hints of engineered behavior. Those suggestions would force us to reconsider what kind of object we are observing when we point our instruments at 3I Atlas. It is important to stress that such extreme interpretations are not supported by mainstream science. The dominant view is that 3I Atlas is an unusual but natural comet, and that any brightness changes are driven by physical processes we can, in principle, understand. However, we are in an unusual situation. We are dealing with an interstellar object, with a very small number of previous examples, trying to fit its behavior into patterns derived mostly from comets native to our own system. Where there is limited data and real uncertainty, speculation tends to grow. That is the gap in which online debates, alternative theories, and dramatic narratives find room to spread. The disagreement over brightness will not cleanly resolve before December 19th. We are likely to reach closest approach with multiple narratives still active. One in which 3I Atlas behaves like a complex but natural comet, and another in which hints of structured variation are treated as signs of something more. Both amateur and professional observers will look at the same sky and, because of their tools, assumptions, and thresholds for evidence, may continue to see different things. For many people, that ambiguity itself, rather than any confirmed anomaly, may be what feels most unsettling when they step outside and look up. Alongside the brightness question, there is a second area where 3I Atlas has drawn careful attention: its path through space. Objects in space obey the laws of gravity. Their motion can be described with equations that relate position, velocity, and time. Using those equations, we have predicted planetary locations, guided spacecraft into orbit, landed rovers on Mars, and flown probes through narrow gaps in the rings of Saturn. When an interstellar object enters our solar system, we expect to be able to plot its course with similar precision, tracing its past path and its future exit with confidence. 3I Atlas follows what is known as a hyperbolic trajectory. When an object is gravitationally bound to the Sun, it travels on an elliptical orbit and can return again and again, like long-period comets that revisit the inner solar system after many years. A hyperbolic path is different. It describes a one-time pass. The object comes in, swings around the Sun once, and then leaves, never to return, because it has more than enough speed to escape the Sun's gravity. In the case of 3I Atlas, the calculations are clear on this point. It came from interstellar space, it is passing through our neighborhood, and it will eventually head back out into the wider galaxy. The more complicated part of the story concerns the small deviations from the path that pure gravity would produce. Comets are not solid, unchanging bodies. As they warm up near the Sun, their ices turn into gas and escape. These jets of gas act like tiny rocket engines, pushing the nucleus in directions that depend on where the active regions are located and how the object is rotating. These effects are called non-gravitational accelerations. Astronomers expect them and routinely include them in orbit calculations for comets. For 3I Atlas, we know that outgassing is happening because we see the coma rich in carbon dioxide. In principle, that should allow scientists to estimate the size of the effect and fold it into their models. The nucleus of 3I Atlas is estimated to be somewhere between about 440 meters and about 5.6 kilometers across. That is a wide range, but it reflects the difficulty of sizing a distant object with unusual reflectivity. By combining these size estimates with measurements of the coma, researchers can build models of how much thrust the outgassing should provide. From there, they can compute how much the actual trajectory should differ from a path controlled only by gravity. For most research groups, when these models are compared with observations, the match is good enough to be considered acceptable. The non-gravitational acceleration appears consistent with what you would expect from a comet of that general size and composition. In that view, there is no need to invoke extra forces. The slight differences between the model and the data fall within normal margins of error for this kind of work. A small number of independent analysts, including some with training in orbital dynamics, see things differently. When they inspect the publicly available data, they claim to find small residuals, tiny differences between the predicted path and the measured positions that do not fully disappear, even after reasonable outgassing models are applied. In their reading, the observed acceleration is just a bit higher than the models predict. The gap is very small, but to them it is statistically meaningful. From this comes a number that has been mentioned quietly in some discussions, a probability on the order of about 0.03% that the current trajectory of 3I Atlas cannot be fully matched by standard comet outgassing models alone. Put another way, they suggest that there is a tiny fractional chance that something else might be contributing to the thrust. It is essential to be clear about what such a number does and does not mean. It is not a claim that 3I Atlas is artificial. It is not a proof of any engineered system. It is a measure of how well a particular mathematical model fits the data. And the argument is that there is a small but non-zero mismatch. In many other contexts, a gap of that size would be easily dismissed as a combination of measurement uncertainty, instrumental limits, and simplified assumptions inside the model. Here, the context is different. We are dealing with an interstellar object, only the second one studied in such depth. The first, called Oumuamua, also showed non-gravitational acceleration that was hard to explain in simple terms. Oumuamua had no detectable coma, no obvious gas or dust that could provide thrust, yet its path shifted in ways that looked like a gentle push. Researchers proposed several natural explanations: invisible outgassing of very light gases, pressure from sunlight on an unusually reflective surface, or structural effects from internal stresses. All of these required conditions that were not typical of familiar comets. Most scientists accepted that, given the limited data, such natural explanations were the most reasonable. A minority continued to argue that Oumuamua's behavior was difficult to fit into standard models. Now, with 3I Atlas, some people see an echo of that earlier case, although on a much smaller scale. The unexplained component of the acceleration, if it exists at all, is tiny and buried near the limits of our ability to measure. Yet, for those inclined to look for patterns, it becomes another hint that interstellar visitors might not behave exactly like the objects we have studied for centuries. There are many possible natural reasons why this could be true. The long journey through interstellar space may change these bodies in ways we do not fully understand. Constant bombardment by cosmic rays, repeated cycles of extreme cold, broken by brief periods of heating near stars, and slow internal changes could all produce unusual internal structures or surface layers. These, in turn, could influence how and where gases escape when the object warms up, which would alter the resulting accelerations in ways that are hard to predict. There is also, again at the very edge of serious discussion, the more speculative idea that slight anomalies in the trajectory could hint at some form of intentional control. This does not mean dramatic maneuvers or obvious course changes. The picture some people imagine involves subtle stabilization with mass distribution or venting patterns arranged so that the object tends to orient or move in particular ways. It could be as simple as an asymmetric pattern of vents that always produces a small net thrust in a chosen direction, or an internal structure that responds differently to external forces than a uniform lump of ice would. Mainstream science does not claim that this is what is happening with 3I Atlas. The dominant view is still that non-gravitational acceleration arises from natural outgassing, shaped by the object's size, composition, and rotation. The point, rather, is that the current data leave a narrow opening. The mathematical description of the trajectory fits well, but perhaps not perfectly. That small imperfection is enough for some people to imagine alternatives. In that sense, the equations leave the door open just a crack, and through that narrow opening, speculation continues to seep in. That tiny, non-zero probability matters, because in a universe described by statistics, anything that is not strictly zero remains possible. For a global population that has spent decades surrounded by science fiction, documentaries, and online speculation about the cosmos, even a very small chance becomes a hook for the imagination. It becomes a loose thread that, once pulled, can start to loosen our comfortable assumptions about what 3I Atlas really is. Instead of being only an interesting but ordinary comet from another star system, it becomes a kind of code, an object that might carry more meaning than we yet know how to read. Over the next weeks and months, as 3I Atlas continues its journey outward, more observations will be made and more careful calculations will refine its path. That small probability could effectively vanish as the models and measurements line up more cleanly, or it could grow slightly if new data keep pushing in the same direction. Either way, we are learning that interstellar space is not empty, that visitors from other stellar systems arrive more often than we once believed, and that each one forces us to face questions we are not entirely ready to answer. If somewhere, in offices and facilities most of us will never see, people are watching. 3I Atlas, with more than simple scientific curiosity that would not be surprising. The details of that kind of attention are rarely shared in public, but we can think through what such a response might look like. Science, in its public form, is designed to be open. Observatories publish their measurements. Research groups submit papers to journals, where other scientists review and test their claims. When important discoveries are made, they are announced in press releases, conferences, and public talks as part of a shared human effort to understand the universe. Alongside this visible layer, there is another layer of observation that almost never appears in astronomy, bulletins, or agency news feeds. It involves instruments built for other purposes, which can be quietly pointed at the sky when something unusual appears. Some people have suggested that something like a passive observation protocol is now in effect for 3I Atlas. In this idea, passive means there is no active probing that would reveal our interest, no radar pulses aimed at the object, no powerful beams announcing that we are watching. Instead, the focus is on listening and on looking, gathering every photon of light, every radio wave, every possible hint that reaches Earth from the direction of this interstellar visitor. Protocol implies a pre-planned set of steps for how to respond when something enters the solar system that does not quite match the usual categories, and a designation like the letter Z is sometimes used, at least in fiction and planning documents, for contingency plans that people hope they will never need. The label itself is speculative, but the idea of having such a playbook is not. We do know from public information that 3I Atlas has received unusual attention from space-focused organizations. The International Asteroid Warning Network, which normally devotes its time to objects that could come close to Earth, has set aside resources to monitor this comet, even though its impact probability is effectively zero. Spacecraft designed for heliophysics, the study of the sun and the solar wind, have taken images of 3I Atlas as it moves through the inner solar system. This is the first time such instruments have recorded an interstellar object, creating a new kind of dataset that combines solar physics with the study of a visitor from another star. The scale and continuity of this coverage suggest an effort that goes beyond casual curiosity. Beyond the open scientific world, there are deep space monitoring systems that serve more than one purpose. Large radio telescopes that listen for signals from distant galaxies or search for hints of extraterrestrial intelligence can also detect artificial transmissions or structured radio emissions from objects closer to home. Very low-frequency arrays built to study Earth's magnetic environment and upper atmosphere can sometimes pick up unusual electromagnetic signatures from space, including interactions between plasma and cometary material. These instruments were not built for 3I Atlas, but they can be redirected. The data they collect do not always appear in public archives, at least not right away. It is important to be precise here. There is no verified evidence that intelligence agencies have received signals from 3I Atlas. There is no confirmed proof that this object is anything other than a natural comet. What is reasonable to say is that if an interstellar visitor raises scientific questions and becomes a topic of public interest, it would be unusual if security and intelligence organizations did not at least pay attention. Their role includes monitoring potential threats, evaluating unknowns, and gathering information about anything that might have implications for national or global security. An object from another stellar system moving through our neighborhood, perhaps behaving in slightly unexpected ways, fits within that range of concern. Some online communities, especially groups that blend amateur astronomy with fringe science topics, have reported curious findings. A few hobbyist radio monitoring stations claim to have detected odd, very low-frequency noise that seems to line up in time with reported brightness spikes from 3I Atlas. These reports are anecdotal and unverified. They could easily be caused by local, electrical interference, equipment issues, or unrelated signals. Still, they are persistent enough to show that many people are watching and comparing notes. Even if the specific claims do not hold up, the effort itself can sometimes uncover patterns that no single observer would have noticed. History shows that military and scientific observation of the sky have often overlapped. During the Cold War, sensors meant to detect nuclear tests in the atmosphere and in space recorded the light and energy from a large meteor explosion over the Soviet Union. Those data, later made available to scientists, helped improve our understanding of how often large objects strike Earth and what kind of damage they can cause. In more recent years, classified instruments have detected incoming meteors that were never seen by public networks, with their data only shared openly after a delay. The link between security systems and cosmic events has always been closer than most people assume. If similar systems are now pointed at 3I Atlas, the results might not become public for a long time, if at all. There are several reasons why such observation might be kept quiet. One is the desire to avoid early statements that could lead to panic or misunderstanding. If instruments detect something that looks strange, those signals need to be checked and rechecked before anyone makes strong claims. Another reason is the wish to maintain an informational advantage. If there is even a remote chance that an object could represent more than a normal comet, some decision makers might prefer to collect as much data as possible before letting others know what they are seeing. A third reason involves international relationships. Space is increasingly a domain of competition and cooperation between nations. A major finding connected to an interstellar object could influence how countries think about space security, planetary defense, and shared response protocols. There is also a less dramatic, but very practical, possibility. Monitoring 3I Atlas with a wide range of instruments could be a rehearsal. It could be a way to test detection networks, data sharing systems, and coordination between different agencies and countries. In this view, the comet is important not only for its own properties, but as a chance to practice for future events. If another interstellar object arrives on a trajectory that is less friendly or shows clearly unusual behavior, we will need tested procedures for quick assessment, internal communication, and responsible public messaging. As the date of closest approach draws nearer, somewhere in secure facilities with controlled access, people are almost certainly watching 3I Atlas with great care. They are recording streams of data that may never appear in open databases, running analyses that will not be written up in ordinary journal articles, and asking questions that might sound overly cautious in public conversations. From their perspective, it is better to be ready for rare situations that may never occur than to be caught unprepared by the one that does. All of this connects to a more immediate issue. What happens in the last few days before 3I Atlas is at its closest point. As any deadline approaches, time seems to compress. Months of tracking the object, collecting measurements, and fine-tuning models shrink into a narrow window in which decisions must be made using incomplete information. For 3I Atlas, that critical window is often described as the first 72 hours before closest approach on December 19th. During that period, uncertainty tends to be at its highest, and the gap between what we know and what we wish we knew becomes very important. In that 3-day span, planning shifts from abstract discussions to concrete actions. Governments and institutions that take low probability, high impact risks seriously have playbooks for moments like this. For an interstellar object with essentially no chance of hitting Earth, but with behavior that is not fully understood, those plans usually begin with a final round of data consolidation. Observations from many telescopes and spacecraft are gathered into a single, updated picture of the object's position, path, brightness, and composition. Teams at different observatories and agencies contribute their data and their analysis, building a combined view that no single group could create alone. These merged datasets are then passed to modeling groups, which run simulations not only for the most likely outcomes, but also for less likely scenarios. They explore the tails of the probability distribution, looking for cases in which the comet might behave in ways that require particular responses, even if those cases are unlikely. At the same time, another kind of planning is taking place: the development of a communication strategy. Someone has to decide what will be said to the public, when it will be said, and how. Should the message focus on the scientific consensus that 3I Atlas appears to be a natural comet whose path does not pose a threat? Should speech and statements talk openly about the uncertainties and the conflicting data that have fed speculation? Should official voices directly address fringe theories, or should they ignore them in the hope that they fade on their own? There are no simple answers to these questions. If officials choose words that sound too alarming, they may feed panic or invite sensational coverage. If they offer only calm reassurances and dismiss all concerns without explanation, they may fuel mistrust and reinforce the idea that important details are being hidden. Getting this balance wrong in those final 72 hours can either raise anxiety that did not need to exist, or create a feeling that legitimate questions are being brushed aside rather than taken seriously. In that final 72-hour window, there is also a third layer of preparation that can sound overly cautious until you think carefully about why it exists. This layer is about operational readiness. During this period, communication systems come under extra review. The satellites that carry internet traffic, global positioning signals, and financial data all depend on precise timing and reliable links. If there were even a small chance that 3I Atlas could be linked to electromagnetic effects, plasma interactions, or other space weather phenomena that might disturb those systems, this would be the time to make sure backup options are ready. The point is not that trouble is expected, but that the cost of being caught unprepared can be far greater than the cost of putting redundant systems on standby that never end up being used. Emergency services can also receive briefings that might sound excessive when you remember that impact risk is effectively zero. But officials have to think not only about physical danger, but about how people react. If 3I Atlas suddenly becomes visible to the naked eye, if social media fills with dramatic claims and confusing images, if the story shifts in the public mind from known comet to mysterious object, then first responders may face a different kind of strain. They may need to handle a spike in calls to emergency numbers from people worried about what they see in the sky, or from those who think they see related signs and omens. There could be more traffic accidents caused by drivers who are looking upward instead of watching the road. Mental health services might see more crisis calls from individuals whose sense of reality is already fragile and who interpret the sight of a strange object as proof that their fears or extreme beliefs are correct. None of this is guaranteed, but it is the kind of social ripple effect that planning offices are paid to consider. Networks built to watch for hazardous asteroids and meteors may also move to a higher state of alert in this same period. This change in posture would not be because 3i Atlas is on a course to hit Earth, but because its passage offers a real-world test of their systems. If you are responsible for planetary defense, you want to know that your sensors, data pipelines, and international partnerships work smoothly when an unexpected object passes through. You want to see how quickly new observations can be processed, how fast warnings can be shared if they are ever needed, and where weak spots still exist. 3i Atlas is a rare chance to run that test not with a computer model, but with an actual interstellar body moving through the inner solar system. The psychology of this kind of preparation is delicate. Groups planning for uncertain events constantly try to balance reasonable readiness against the risk of creating their own anxiety. If they do too little, they may be caught unready if something truly unusual happens. If they do too much, they risk sending signals that something is wrong, which can itself cause stress, rumors, or overreaction. The aim is always a level of response that feels proportional to the probability of an event, adjusted for how serious the consequences would be if it did occur. In the case of 3i Atlas, the chance of anything deeply anomalous remains low, but the potential impact of being completely unprepared for a rare event that is visible in the sky to many people at once is high enough to justify more than casual attention. It is worth asking what kind of events would count as truly anomalous in this context. One possibility would be a sudden jump in brightness, large enough that millions of people around the world can see the object at roughly the same time, making it an instant topic of conversation. Another would be small but clear changes in the trajectory that, while not pointing toward Earth, still suggest that the motion cannot be explained by gravity and simple outgassing alone. A third category would be the detection of structured signals in radio or in light that do not look like random noise or natural reflections. Fragmentation is another scenario, the nucleus breaking apart into several pieces, revealing interior layers or creating multiple objects where there was only one. Any of these possibilities, even if they pose no direct threat, would rapidly change how both scientists and the public talk about 3i Atlas. The object would move, in many minds, from an interesting visitor to a phenomenon that demands fast explanation. Talking about preparation in public demands the same kind of balance. If agencies urge people to be ready without giving clear reasons, they invite rumor and fear. If they focus too much on unlikely scenarios, they risk making very low probability outcomes seem more likely than they are. Most organizations try to communicate in a way that is honest about what is known and not known, calm about the absence of physical danger, and respectful of real questions. They try to avoid tones that sound dismissive or condescending, because those can make mistrust worse. Whether that balance holds as the last days before closest approach pass will depend on how the data change and whether the region of uncertainty in the models grows tighter or remains wide. For individuals, the question of, what should I do, as December 19th approaches, is tied to personal views on uncertainty and control. From an objective, physical risk standpoint, there is no credible reason for special, personal action beyond the kind of general preparedness that is useful in many situations. Some people, however, feel calmer when they take small steps that give them a sense of readiness even for unlikely events. They may review how they would reach family members if communication networks were briefly disturbed. They might keep offline copies of key documents or contact lists. They might choose to follow updates from trusted scientific sources rather than rely on fast-moving posts from social media feeds. These are not extreme measures. They are basic, steady habits that apply to many possible disruptions, whether caused by storms, technical failures, or unexpected events in the sky. If December 19th passes with nothing more dramatic than new research papers and updated light curves, then these preparations will simply have been part of routine caution. There is no harm in that. If, on the other hand, the 72-hour window reveals behavior we did not expect, those same modest actions may be more helpful than anyone hoped they would need to be. All of this leads naturally to a broader question about our technological world and how it responds to electromagnetic surprises. Modern life depends deeply on the controlled use of electricity and magnetism. Every device, every communication link, every digital system that underpins transportation, finance, healthcare, and daily life relies on the quiet movement of electrons and on electromagnetic waves carrying information at the speed of light. We have built these systems under the assumption that the electromagnetic environment of near-Earth space is mostly stable, apart from occasional solar storms that we understand reasonably well. When an object from outside our solar system, with a chemical makeup and surface history unlike anything we have studied up close, enters that environment, it is natural to ask what, if any, electromagnetic effects it might generate. For 3I Atlas, we start with what we know. The comet has a coma dominated by carbon dioxide, a broad cloud of gas and dust that extends thousands of kilometers around the solid nucleus. As solar ultraviolet light strikes this gas, it ionizes some of it, stripping electrons from atoms and molecules. The result is a plasma, a state of matter in which charged particles move in response to electric and magnetic fields. The solar wind, a constant flow of charged particles from the sun, interacts with this plasma. It bends magnetic field lines around the comet, forms a kind of plasma tail pointing away from the sun, and creates a complex electromagnetic structure that changes with solar activity and with the comet's position. All of this is familiar. We have seen similar structures around many comets that originated in our own solar system. What may be different about 3I Atlas is the long history it brings from interstellar space. Research suggests that over millions or even billions of years, bombardment by high-energy cosmic rays in deep space could transform the outer layers of the comet. Cosmic rays are mostly high-energy protons that slam into matter at nearly the speed of light, breaking chemical bonds and triggering new reactions. Over vast timescales, this process could build a thick crust, rich in complex organic molecules and altered ices. Comets that spend their whole existence in the solar system are somewhat shielded by the sun's magnetic field and by the heliosphere, the bubble of plasma around our star. An interstellar comet, by contrast, would have spent long periods in regions where the full force of galactic cosmic rays can work on it. When such a crust is finally heated near a star, it can behave in ways we have not yet measured directly. As jets of gas punch through it and as parts of it sublimate, the pattern of charges and currents might differ from what we expect based on normal comets. This raises the question of electromagnetic pulses, or EMPs. In public conversation, an EMP usually means a sudden burst of electromagnetic radiation strong enough to induce harmful currents in electronic systems, possibly damaging them or disrupting their operation. Large EMPs are usually linked either to nuclear explosions in the atmosphere, which produce intense gamma rays and secondary electrons, or to powerful solar eruptions that hurl charged particles toward Earth. 3I Atlas is not a nuclear device or a star. It is not producing that kind of energy. What it is producing is a localized plasma environment with magnetic structures, moving charged particles, and potential for rapid changes when outgassing events occur. When a pocket of volatile material suddenly turns to gas and bursts outward, it does not only create mechanical pressure, it also pushes charged particles through magnetic fields, which can generate electromagnetic disturbances. These disturbances are expected to be small compared with a solar storm and are spread out over a vast region of space. At a distance of about 1.8 astronomical units from Earth, any such disturbances from 3I Atlas would almost certainly be far too weak to have a noticeable effect on our planet's surface or on satellites near Earth. They would be local to the region around the comet itself. If a spacecraft were flying close by, engineers would need to understand that environment. In this case, no mission is planned to pass near the comet, so its electromagnetic environment remains of scientific interest rather than immediate operational concern. The reason to talk about this at all is not because 3I Atlas is expected to cause damage, but because it highlights the blind spots that arise when dealing with objects from beyond our usual experience. We do not yet have direct measurements of the electromagnetic conditions in the immediate surroundings of 3I Atlas. We do not know in detail how its irradiated crust behaves as it warms, or exactly how its jets of gas shape local electric and magnetic fields. In the absence of direct data, we rely on analogies to solar system comets. Those analogies are useful, but they may not be perfect. Within the range of that uncertainty, there is room for small, unexpected phenomena. This is where the idea of Faraday defense comes in. A Faraday cage is a simple but powerful concept in physics. It is a closed conductive shell that shields its interior from external electromagnetic fields. When electromagnetic waves hit the conductive material, they cause charges in that material to move. Those moving charges produce fields of their own that cancel the incoming field inside the enclosure. The electronics or other sensitive components placed inside remain protected. In practice, a Faraday cage can be built from any reasonably continuous conductive container, from specially designed enclosures used in laboratories to something as simple as a tightly sealed metal box. At the level of households or small organizations, Faraday protection is less about building perfect cages and more about sensible habits. Unplugging devices during periods of known electromagnetic disturbance, such as major solar storms, reduces the chance that voltage spikes will damage them. Using surge protectors and power conditioners helps smooth out sudden changes in line voltage. Keeping offline backups of important data reduces dependence on networked systems that could be interrupted. These steps are not extreme. They are part of a general approach to resilience in a world where many important things run on electricity and code. In that broad picture, 3I Atlas is not a likely source of serious electromagnetic trouble. Its distance, its size, and our current understanding of comet physics all point to its effects being minor at Earth. But thinking through its possible electromagnetic behavior is still useful. It reminds us that our civilization rests on assumptions about the environment around our planet, and that rare or new events can test those assumptions. The same principles of Faraday defense and careful preparation apply whether the disturbance comes from a solar storm, a failure in the power grid, or, in the very unlikely case, a subtle effect linked to an interstellar comet passing through our sky. At the level of whole societies, the question of electromagnetic protection does not begin or end with 3I Atlas. Power grids, communication networks, and financial systems all depend on equipment that can fail if exposed to strong enough electromagnetic disturbances. Engineers already design redundancy into these systems. They add backup lines, protective circuits, and failover plans so that a fault in one place does not bring down the whole system. Much of this work is driven by concern over space weather, especially severe solar storms. One event is often used as a reminder of what the Sun can do. In the year 1859, a massive solar storm, now called the Carrington event, sent currents surging through telegraph wires, starting fires and shocking operators. It showed that Earth's electromagnetic environment can, at rare times, become hostile to technology. Could 3I Atlas produce anything on that scale? The answer is no. The energy released in a solar superstorm involves the entire Sun, with magnetic fields storing energy for days or weeks, and then releasing it in a powerful burst. Particles are accelerated to high speeds, and shock waves travel across the solar system. By comparison, the jets from a comet, even one with unusual composition, operate at tiny fractions of that energy. Thinking through electromagnetic readiness in the context of 3I Atlas is still useful. It is not because this comet is expected to cause damage, but because the same habits that make infrastructure resilient to space weather also help in other kinds of disruption. It is a way of accepting that space is not empty and harmless. It sometimes throws technical challenges at a civilization that runs on electricity and signals. The most likely outcome is that 3I Atlas passes without causing any effect on Earth, that our instruments can link to electromagnetic activity. We may measure its local plasma environment, model its interaction with the solar wind, add a new data point to comet physics, and move on. But the most likely outcome is never the only possible one. Low probability events do happen over long timescales. When they do, the difference between a major crisis and a manageable inconvenience often depends on whether anyone prepared for unlikely possibilities in advance. In that sense, Faraday protection and related measures are less about building bunkers and more about recognizing a simple fact. Our machines operate in an environment we do not fully control, and occasionally that environment reminds us of that. This leads to a different, more speculative question that few officials address openly: the biological question. Life on Earth began as chemistry. The basic building blocks, amino acids, nucleotides, simple lipids assembled over long spans of time into systems that could copy themselves, change, and evolve. These molecules did not appear from nowhere. They formed through chemical reactions in environments rich in the right ingredients. That raises a natural question. Are those ingredients unique to Earth, or are they common in the wider universe, carried between stars on objects like 3I Atlas? What we know so far about the comet's composition is already striking. Observations from the James Webb Space Telescope show a coma made of carbon dioxide, water, carbon monoxide, dust, and a mix of other ices. Studies of how cosmic rays affect matter in deep space suggest that the nucleus likely has an outer layer rich in organic molecules, compounds containing carbon, built by radiation, acting on simpler ices over millions or even billions of years. It is important to be clear: organic molecules do not mean life. They simply mean carbon-based chemistry, which is widespread in the universe. But organic molecules are also the raw material from which life can, in principle, emerge under the right conditions. The idea that life or its ingredients can move between worlds is known as panspermia. In one version, comets, asteroids, and dust grains carry prebiotic molecules from one planetary system to another. In some more extreme versions, they might even carry hardy microorganisms. Scientists have debated these ideas for more than a century. Supporters point out that impacts can throw rocks into space, and that some microbes on Earth can survive harsh conditions for long periods, skeptics focus on the obstacles. Interstellar space is harsh. High-energy cosmic rays destroy complex molecules. The vacuum and wide temperature swings between near absolute zero and intense heating near stars would damage anything not deeply buried. The mainstream expectation is that even if 3I Atlas once carried any biological material from its birth system, that material is now long dead. It would have been sterilized by radiation, broken apart by impacts with dust, and changed beyond recognition by physical and chemical stress. The organic molecules we detect are probably products of radiation chemistry, new compounds formed when cosmic rays break simpler ices and the fragments recombine. This is fascinating chemistry. It may even be relevant to prebiotic processes, but it is not life. It is not a cargo of living organisms capable of waking up and multiplying if they reach Earth. There is, however, an edge case scenario worth considering as a thought experiment. The radiation that alters surface material only penetrates so far. Depending on composition, cosmic rays might reach a depth of several meters, maybe tens of meters. If the nucleus is several kilometers across, its deep interior could, in principle, remain more shielded. In that protected core, chemistry might have followed a different path, with complex organics forming under conditions that we have never sampled. As the comet warms, outgassing could expose small pockets of this interior material or release tiny grains into space. If that were the case, 3I Atlas would be more than just another comet. It would be a natural sample return mission from another star, delivering chemistry we cannot find anywhere in our own system. In such a scenario, advanced spectroscopy, precise study of how the comet absorbs and emits light at different wavelengths, might detect unusual organic signatures. These could include molecules with structures not typical of known comet chemistry, or isotopic ratios that signal formation under different conditions than those in our solar nebula. So far, no such clear anomalies have been reported. The published results describe a comet whose composition mostly fits within the range of known physics, apart from its high carbon dioxide content. Spectroscopy has limits. It is most sensitive to abundant materials and to molecules that have strong, clear spectral lines in the wavelength bands we can observe. Rare components, deeply buried layers, and complex molecules that do not leave strong fingerprints might remain hidden. When people talk about risk in this context about possible biological hazards from interstellar material, they are mostly in the realm of fiction. Earth has been hit by comets and asteroids for more than 4 billion years. Many of those bodies came from the outer solar system. Some may have been captured from interstellar space early in the sun's history. If there were a simple path from such impacts to global biological catastrophe, our biosphere would likely show evidence of it. Instead, what the record suggests is that impacts and incoming material helped supply the raw ingredients for Earth's own biochemistry. Studies of meteorites support this. Certain types of meteorites, especially carbon-rich ones, contain amino acids and other organic compounds. Their discovery showed that prebiotic chemistry happens in space, and that the building blocks of life are not unique to one planet. Yet these meteorites did not pose biological threats. The molecules they carried were not living organisms. They could not replicate or spread on their own. They were chemical clues, not agents of disease. 3I Atlas almost certainly falls into the same general category, even if it carries complex organic chemistry shaped under alien conditions. That chemistry is not, by itself, a biological hazard. It could teach us about how molecules behave and evolve in other stellar environments. It could help us understand how common the ingredients for life are, but there is no evidence that that it represents a threat in any direct biological sense. The deeper reason these questions resonate is philosophical. They touch on whether Earth is an isolated case or part of a wider network. Are we a unique experiment in one small corner of the galaxy, or are we connected to a larger flow of matter and chemistry between stars? If 3I Atlas contains organic material unlike what we see in most solar system bodies, that points toward connectivity. It suggests that stellar systems trade material more often than we once thought, through comets, asteroids, and perhaps rogue planets that wander between stars. Imagine, as a thought experiment, that we had the ability to send a probe to 3I Atlas, land on its surface, drill deep into the nucleus, and return samples from its interior. What would we see when we opened those containers? Perhaps we would find the expected mix of frozen carbon dioxide, water, and other simple ices, with isotopic ratios and molecular patterns that match our models. Or perhaps we would find chemistry that does not quite fit, with molecules arranged in ways we did not predict, hinting at conditions we have not recreated in any laboratory. In the most speculative version, we could even find molecular structures that look highly organized, complex enough to make us wonder how they formed. In practice, we will not get that sample from 3I Atlas. The object was identified too late and is moving too fast for a realistic mission to catch it during this passage. By the time we could build and launch a dedicated spacecraft, it would already be on its way back into interstellar space. The questions it raises, however, will remain. They will be asked again each time we discover a new interstellar visitor, until we develop the capability to study one of them up close. Behind the technical details lies a broader shift in perspective. The more we learn about interstellar comets, the harder it is to see the galaxy as a set of isolated islands. Instead, it begins to look like a connected system with shared chemistry and, perhaps in some places, shared biology. If we eventually find evidence that life's ingredients, or life itself, can move between systems, then the cosmos becomes not just a stage for physics and chemistry, but a place where those processes can, under the right conditions, give rise to something more. That something more brings us to the edge of a different topic: how human societies respond when core assumptions about their place in the universe are challenged. For now, we are still dealing with possibilities and unknowns. But we can already ask the question, what would happen to our collective mind if we ever confirmed that an object like 3I Atlas was not only interstellar, not only rich in exotic chemistry, but clearly artificial, an artifact? Human consciousness rests on deep assumptions, so basic we rarely notice them: that the sun will rise, that gravity will act as it always has, that the universe follows stable laws. When an event forces us to reevaluate such assumptions, the result is more than individual surprise. It is a kind of shock that sweeps through the shared mental space of a civilization. Psychologists sometimes call this paradigm shock, a sudden need to update our mental model of reality. For an entire society, the effect is broader. You could call it a shock to the psychosphere, the invisible field of shared beliefs and expectations. To understand how that might feel and how people might react, it helps to look at earlier moments when the human picture of the cosmos had to change. Let me give you some historical context. When the first atomic bomb test took place in 1945, it did more than prove a new type of weapon. It forced humanity to face the idea that we now held the power to destroy ourselves. That realization reshaped global politics, philosophy, art, and culture. 2 decades later, in 1969, the first moon landing did more than put human footprints on another world. The images of Earth as a small, fragile sphere hanging in darkness changed how many people thought about planetary limits, environmental responsibility, and human unity. Both events produced shocks in the shared mental world of our species. The story we told ourselves about what humans can do and what kind of universe we live in had to be rewritten. Now imagine that December 19th passes and something about 3I Atlas forces a similar adjustment. Not necessarily a clear announcement that it is an alien spacecraft, but a solid, well-supported conclusion that its structure, motion, or physical behavior cannot be explained with current comet models. News of that conclusion might appear first in an official briefing, or might leak through less controlled channels. Either way, within hours, billions of people could be confronted with the possibility that an object from another star system is more than just ice and rock. The psychological effect would not be simple. Some people would feel intense excitement and curiosity. For them, the discovery would mean that humanity has crossed an invisible line, moving from a stage where we can guess about the wider galaxy to a stage where we are directly interacting with it. Social networks would fill with attempts to interpret what the data mean, debates over what to call the object now, and arguments about whether this is good news or bad. Others would respond with fear or deep unease. When something challenges the basic structure of your worldview, it can feel threatening even if there is no physical danger. The unknown, especially on a cosmic scale, can be hard to fit into everyday life. People who already carry anxiety about the future might see the event as a sign that the world is slipping out of control. Religious communities would move quickly to interpret the news. Some might see it as a confirmation of long-held beliefs or prophecies, a sign that fits into existing narratives. Others might struggle to fit interstellar artifacts or non-natural objects into doctrines that assumed a simpler picture of the universe. This kind of rapid reinterpretation can create internal tension and public debate within and between religious groups. People who follow conspiracy theories would likely feel vindicated. Many of them already believe that authorities hide information about unknown objects in the sky. A sudden announcement that 3I Atlas is not what we thought could be taken as proof that they knew all along. New stories would appear, claiming that contacts have been ongoing for years, or that the object has been guided toward us on purpose. These stories can spread very quickly, sometimes faster than careful explanations from scientists. Economic systems would react too. Financial markets do not respond only to material events. They respond to uncertainty and to changes in expectation. A discovery that seems to open an entirely new category of risk or opportunity, one that traders have no model for, would likely cause short-term turbulence. Investors might pull money out of riskier assets until they see how governments and central banks respond. Currency values could shift. Supply chains might feel small shocks if certain sectors slow their activity while waiting for clarity. The disruption need not be extreme to be noticeable. It would become another example of how human systems respond when the unknown suddenly becomes more present. Trust in institutions would be tested if, in the weeks leading up to the announcement, officials had repeatedly emphasized that 3I Atlas was behaving like a normal comet. People would ask why the new information was not shared earlier. If early signs of anomaly come from leaks or outside researchers before any official acknowledgement, suspicion would grow about what was known and when. Even if the delay is due to a genuine need to verify data, the gap between expert knowledge and public awareness becomes a breeding ground for suspicion. Information spreads through social networks in patterns sometimes called cascades. When people see many others around them reacting in a certain way, preparing for disruption, questioning official statements, or interpreting the event as a sign of impending change, they become more likely to do the same. This can create feedback loops if enough people start stocking up on supplies, just in case. Small shortages can appear, which then seem to confirm that something big is happening. If enough people publicly declare that they no longer trust official sources, that shared distrust becomes a reality, even if the original reasons were weak. Social media systems are designed to keep attention. They tend to promote content that triggers strong emotion, fear, anger, excitement, hope, because such content leads to more clicks and shares. In a situation where humanity is suddenly confronting a possible alien artifact or a non-natural object from another star system, posts that frame the event in extreme, simple terms would have an advantage over nuanced explanations. Minority views that are emotionally intense could be pushed into the spotlight more often than calm, middle ground analyses. We can look at past crises to guess how this might unfold, but the parallels are limited. Pandemics show a mixture of cooperation and selfishness, trust and mistrust, clear information and rumor. Wars and large attacks show how quickly daily routines can shift when a threat is perceived as immediate and physical. But 3i Atlas, in this hypothetical, is not a disease or an army. It is a change in our picture of the cosmos. We do not have many direct examples of how societies respond to that kind of shift. The slow realization over the 20th century that Earth orbits an ordinary star in a vast galaxy was spread over decades. People could absorb that idea gradually. A sudden, clear confirmation of a non-natural interstellar object would compress that process into days. Institutions would have to choose how to handle information in those early hours and days. A strategy of tight control, where data are released slowly as understanding grows, might reduce immediate panic, but would also risk accusations of secrecy when more details come out. A strategy of full transparency, where all measurements, uncertainties, and disagreements between experts are made public at once, would support trust in the long term, but might create short-term confusion among people who do not have the background to evaluate conflicting signals. Both strategies carry costs. The choices made by governments, space agencies, and major scientific bodies in that moment would shape public attitudes for a long time afterward. People would remember not only what was discovered, but how they were told. It is important to stress again that what we are discussing here is a thought experiment. The most likely outcome is that 3i Atlas is indeed a natural interstellar comet. It will probably pass through the inner solar system, give us valuable science data, and leave behind only a trail of papers and the memory of many speculative conversations. In that case, the main lesson will be how much imagination one object from another star system can trigger. Even if that is how things play out, thinking through our possible responses to a future, more dramatic discovery has value. Interstellar objects will continue to arrive. At some point, whether in our lifetime or much later, humanity may find clear evidence of life beyond Earth or of technology not made by us. How we react in that moment will depend in part on whether we have already considered the possibilities, built frameworks for response, and practiced balancing wonder with caution. 3i Atlas, whatever it turns out to be, offers a preview of this challenge. If a true psychosphere shock comes at some future time, a day that divides history into before we knew and after we knew, our ability to handle it without tearing our social fabric will depend on the resilience we have built beforehand. Thinking in these terms leads to another question about control, not of objects in space, but of information on Earth. Throughout history, control of communication has been a key tool of power. Rulers have limited who can print books, governments have censored newspapers in times of war, and authoritarian regimes have filtered or blocked internet access to prevent organization and dissent. Today, global communication operates at the speed of light. Data moves across borders in fractions of a second. Many basic functions, from banking to logistics to health services, rely on constant connectivity. That reality raises a difficult question. If something connected to 3i Atlas were to trigger serious concern among leaders, whether because of its nature, its behavior, or its effects on public order, would authorities try to manage the situation by restricting communication? Do they have the capability to do so on a large scale? And if they did, what would it look like in practice? The idea, often called an internet kill switch, is not usually a single physical button. It is a concept that points to the ability of governments to reduce or cut off access to the internet and other communication systems in a crisis. In some countries, laws explicitly give leaders the power to order such shutdowns during national emergencies. In others, existing emergency or national security laws could be interpreted to allow significant limits on communication. The specific technical tools differ from place to place, but they share a basic feature. Digital networks have bottlenecks and control points, and whoever controls those points has leverage over the flow of information. We have real-world examples. During the 2011 uprising in Egypt, the government ordered major internet service providers to shut down most access, and for a time, connectivity dropped sharply. In Myanmar, authorities have repeatedly restricted internet access in certain regions during periods of conflict. In India, local or regional shutdowns have been used many times in response to protests or tensions. These cases show that, at least in some contexts, governments are both able and willing to interrupt digital communication, despite the economic and social costs. Could something similar be considered in a scenario where 3i Atlas is the trigger? For that to happen, several conditions would likely need to be in place. First, leaders would have to feel real uncertainty or fear about what the object represents or how people are reacting to it. Second, they would have to believe that letting information flow freely would worsen the situation more than it would help, at least in the short term. Third, they would need confidence that restrictions could be enforced without causing a larger breakdown. And fourth, in the case of a truly global event, major powers would need to at least avoid actively undermining each other's measures, because a shutdown in one country does little to stop information if others remain fully open. Technically, the ease of implementing such controls depends strongly on how a country's networks are built. In states where the government owns or tightly regulates the main internet service providers and international connections, shutting things down or slowing them is relatively straightforward. Orders can be issued to a small number of companies or agencies that control the main cables and switches. In more decentralized systems, such as those in many democracies, the internet backbone is spread across many private actors, making coordinated shutdowns harder. Emergency legal powers might still exist, and companies might comply under pressure, but the process is slower and more complex. Satellite-based internet services add another layer. They do not depend on local ground cables in the same way and can sometimes bypass national infrastructure. Governments might still interfere by limiting ground terminals, applying legal pressure, or in extreme cases using jamming techniques. But complete control becomes more difficult as connectivity options multiply. These technical and legal factors matter, but they do not answer the key issue. The more interesting question is not whether authorities could, in theory, restrict communications, but why they would seriously consider doing so in response to anything connected with 3i Atlas. The simple answer to why authorities might try to control communications is to prevent panic. But that is only the surface. The concern would not be that 3i Atlas poses direct physical danger. We have already established that the impact probability is effectively zero. The deeper concern would be social disruption triggered by a sudden shift in how people understand Earth's place in the universe. Imagine a situation where observations clearly show behavior that does not fit natural models. Not vague hints, not noisy data, but strong, repeatable evidence that standard comet physics cannot explain. The moment that conclusion becomes public, social media and news networks would spread it at digital speed. Emergency planners sometimes talk about an information emergency, a situation where the flow of news and interpretation becomes the main driver of crisis. Markets might react sharply to that kind of uncertainty. Stock prices could fall as investors try to reprice risk they do not understand. Social platforms would boost the most dramatic explanations and predictions because those are the ones that keep people engaged. Local officials could be flooded with calls and questions they are not prepared to answer. Religious groups might issue fast, conflicting statements about what the event means. Fringe movements could see it as proof of long-held beliefs and act in ways that add to instability. All of this could happen long before national authorities have time to agree on careful messaging or coordinated responses. In that kind of scenario, the argument for limiting communications, even briefly, would be that it buys time. It would give scientists and officials a window to check the data, clarify what is actually known, and prepare explanations that put the discovery in context. The hope would be to slow the spread of extreme interpretations before they harden into widely held beliefs. The arguments against such measures in open societies are strong. Cutting off or sharply restricting communication is extremely difficult to justify in systems built on the expectation of free access to information. The economic cost would be huge. Many parts of the modern economy, financial transactions, supply chains, remote work, and even basic services depend on continuous connectivity. Interrupting that flow for even a few hours could cause large losses and long-term damage to trust. There is also a political cost. Citizens in democratic states expect to be informed, especially in unusual situations. Being suddenly disconnected would not feel protective. It would feel like being shut out. That feeling can produce anger and suspicion that last long after the immediate crisis has passed. On top of that, complete containment is almost impossible. People find ways around barriers: satellite links, radio, in-person travel, and informal networks. Once information exists, it tends to flow. Because of these problems, some analysts discuss a softer approach instead of an absolute kill switch. That softer approach would involve throttling or filtering rather than total shutdown. Bandwidth for non-essential services, social media, streaming platforms, some entertainment could be quietly reduced. Meanwhile, core infrastructure and access to official information could be kept stable. This would not fully block unverified stories, but it could slow their spread and give more relative weight to carefully prepared updates. We have already seen versions of this in how some countries manage networks during emergencies or times of extreme congestion. It is less visible than a complete blackout and may produce less backlash, yet it can still give authorities some influence over how fast certain kinds of information move. For 3i Atlas specifically, the chance that governments will resort to any form of broad communications restriction appears extremely low. The object does not threaten impact. The scientific uncertainties, while interesting, are unlikely on their own to cause the immediate, global panic that would push leaders towards such extreme steps. Coordinating such measures across many nations at short notice would be very hard. Still, the fact that we can discuss these possibilities seriously and that there are real precedents for network control in other contexts tells us that information management is an important part of crisis planning. For individuals, practical preparation is simpler and not tied to any one event. It means having several ways to reach the people who matter to you: phone, text, email, social platforms, and in some cases an agreed physical meeting place. It means keeping devices charged when you expect possible disruption and having an extra power source if you can. It means knowing where to get information if major networks fail, such as local radio stations, saved documents, and offline maps. These habits are about resilience, not paranoia. They are useful whether the disruption is caused by a storm, a technical failure, or a brief surge of global attention on an object passing through the sky. From here, we can turn to a different kind of possibility, one that many scientists treat with caution, and that much of the public finds compelling: the idea that 3I Atlas might not be a natural comet at all. Instead, it could be a probe or artifact built by some other intelligence. This idea is speculative. It goes beyond what the data can support right now, but it does not come from nowhere. 3I Atlas follows a hyperbolic path that clearly marks it as interstellar. It is not bound to the sun and will not return once it leaves. Its composition, dominated by carbon dioxide with a crust shaped by cosmic ray exposure, is unusual compared with many solar system comets. Its non-gravitational acceleration can be explained by outgassing, yet some analyses suggest a very small mismatch between model predictions and observed motion, leaving a tiny window for other forces. If a civilization wanted to send probes between stars, what might those probes look like? They might not resemble the metal spacecraft we launch. For journeys lasting millions of years, exposed hardware would face constant damage from radiation and micrometeorites. A more durable strategy could be to hide the core systems deep inside a protective shell of ice and rock. The outside would look natural. The inside would hold the machinery. Such a probe might remain largely inert during long periods in interstellar space, using almost no energy while it drifts. It could be designed to wake up when it enters a star's influence, using changes in temperature or radiation as triggers. The same physical processes that shape comets, outgassing, coma formation, changes in spin, could serve as both camouflage and power sources. From the outside, the object would appear to be a comet behaving in mostly normal ways. In that design view, the features we see around 3I Atlas could be intentional. An icy shell acts as shielding. Outgassing creates the appearance of a standard active comet. The small, non-gravitational accelerations could be partly natural and partly controlled, allowing tiny course corrections that are hard to distinguish from normal behavior. The probe could pass through a star system quietly, collect data, and then either transmit it or store it for later, all while drawing little attention. Different probe types have been imagined. A simple reconnaissance probe would carry sensors and memory. It would not need strong engines or bright transmitters. It could record measurements, radiation, radio noise, planetary positions, signs of technology like artificial radio bands, and wait for a suitable time or direction to send that information home in a narrow beam. From our point of view, such a probe could be completely silent. A more complex, self-replicating probe, often called a von Neumann probe, would be designed to use local materials to build copies of itself. As it moves through a system, it might create smaller units, leaving some behind in orbit while others continue. We have not detected anything like that around 3I Atlas, but our observations are limited, and very small or dark fragments could escape notice, especially if they are not emitting signals. There is also the idea of technological debris. Perhaps some civilization, long ago, sent out vast numbers of probes. Many failed, many kept going. Over hundreds of millions of years, some of those objects would be reduced to shells of their original selves, still moving along interstellar routes, but no longer active. 3I Atlas could, in that view, be one such remnant. It would not have been aimed at us. We would simply be seeing a trace of activity from a very distant past, only now visible because our detection abilities have improved. If 3I Atlas were artificial, or partly artificial, what would we expect to see from our current vantage point? One obvious sign would be structured emission, radio or optical signals, with patterns such as regular pulses, shifting frequencies, or coded modulation that cannot be explained by natural processes. So far, no such signals have been confirmed. That does not prove they are absent. We may not be looking at the right times or frequencies, or the transmissions, if any, could be narrowly directed in a way that misses Earth. Another sign would be motion that clearly cannot be explained by outgassing alone. If the object changed direction or speed in ways that require more energy than sublimating ices can provide, we would need to look for another source of thrust. We would also pay close attention to any fragments that appear to separate in controlled ways, behaving more like deployed units than like random pieces breaking off. The counter-arguments are strong and grounded in what we already know. Comets are common outcomes of planetary system formation. Interstellar space likely holds enormous numbers of them, ejected by gravitational interactions over time. As our telescopes become more sensitive, we expect to detect more of these visitors. Unusual compositions can be explained by different birth environments. A carbon dioxide-rich coma, organic-rich crust, and subtle non-gravitational accelerations all fit within the range of what physics allows, given the right initial conditions. From this perspective, invoking an artificial origin is unnecessary. It adds layers of assumption about other civilizations, their goals, and their engineering choices that we do not need to explain the current data. This is why most scientists treat the probe idea as an interesting story to test against evidence, rather than as a conclusion. There is, however, a philosophical angle that keeps the discussion alive. A very advanced civilization designing probes to cross interstellar distances might avoid obvious designs. It might intentionally make them hard to distinguish from natural objects, both to protect them and to avoid influencing younger civilizations. If that is the case, then the probes most likely to succeed would be the ones that look exactly like ordinary comets and asteroids, at least to anyone who is not specifically searching for deeper patterns. That creates a kind of observational trap. The more a probe blends in, the less likely we are to recognize it. We may catalog it, model its orbit, study its coma, and never notice that something about it is engineered. The only way to detect such an object would be to look very carefully for small mismatches between observation and natural models, and then to consider artificial explanations among several possibilities. One suggested framework for this kind of thinking is to ask, if you wanted to study a civilization without disturbing it, how would you design your tools? You would avoid obvious signals or close approaches that could alert or frighten. You would make your probes robust, quiet, and patient. You might have them listen to radio and other emissions, map satellite networks, sample the environment, and then send their findings away in narrow communication beams that are hard to detect unless a receiver is exactly in line. From our current position, we cannot say that 3I Atlas is doing anything like that. We have no confirmed evidence of artificial behavior. What we can say is that the object fits into a category where such questions naturally arise. It is an interstellar visitor with some unusual features. It is passing through a system that now includes a technological species. It may be recording us in ways we do not yet know how to measure, or it may simply be a piece of ancient ice and rock following the rules of physics. For now, as we refine our models and collect more data, 3I Atlas continues on its path, while we continue to debate whether it is only what it appears to be or something more. If 3I Atlas were more than a natural object and somehow able to assess us, what might it find? It would see a species on the edge of becoming truly spacefaring, able to detect and track interstellar visitors, but not yet able to send its own probes to meet them. It would see that we build remarkable instruments while still being tied to one small world, arguing over climate, resources, and borders, even as we begin to think in cosmic terms. From that perspective, humanity might look young and curious, technically capable, but divided, still far from any mature role in a wider community among the stars. I am not saying this is what is happening. The idea that 3I Atlas is an artificial probe remains, at best, a distant possibility, and every observation so far can be explained by natural processes. The value of the hypothesis is not that it is likely, but that it reminds us how incomplete our understanding still is. The fact that we can seriously ask the question shows that the universe is not yet finished surprising us, and that every interstellar visitor carries the potential to challenge what we think we know about Earth's place in the cosmos. There is another way in which 3I Atlas acts as a probe, and this one is firmly within science. It is a probe of our physics. Modern physics rests on assumptions we usually treat as solid. Space and time form a smooth background. Gravity follows well-tested equations. Matter and energy behave according to laws that have survived every experiment we have been able to perform so far. Yet many researchers suspect that at extremely small scales, these assumptions break down. Theories of quantum gravity propose that space-time may be granular or foamy at the tiniest distances, with a structure that our current detectors can barely hint at. As of now, no widely accepted result shows clear evidence of such quantum gravity effects. Some scientists studying gravitational wave data from observatories like LIGO and Virgo have suggested that there may be faint patterns, extra noise that does not fit neatly into known instrumental or environmental sources. They propose that this could be a sign of a deeper structure to space-time, visible only when waves from distant black hole or neutron star mergers pass through. These ideas are speculative. They are debated, unconfirmed, and very much at the frontier of theory. Still, it is worth asking what such effects would mean for an object like 3I Atlas. If space-time really is granular at scales far smaller than atoms, the graininess would average out over ordinary distances and times. For everyday objects, nothing would change, but an interstellar comet traveling at high speed across light years of space might accumulate tiny influences over millions or billions of years. In principle, that could affect how stresses build up inside it, how long certain ices remain stable, or how it responds, in minute ways, to gravity and radiation. Any such effect would be subtle, far below the level of ordinary forces like outgassing and gravitational pull, but not necessarily exactly zero. During its long journey, 3I Atlas has been exposed not only to cosmic rays and dust, but also to whatever the true structure of space-time may be. If quantum gravity effects exist, then the comet's present-day composition and behavior carry a record of those conditions, mixed in with all the other influences. That does not mean we can read that record yet. It does mean that every interstellar object we study is also, in a sense, an experiment that nature has already run for us, integrating tiny effects over immense distances and times. Even if quantum gravity plays no practical role here, the broader lesson is about humility. Our models of comets, of plasma, of orbital dynamics are powerful, but they sit on top of deeper layers of physics we do not fully understand. If we ever found that 3I Atlas's motion or activity contained small residuals that resisted all conventional explanations, we would have to decide whether they are simply measurement errors or hints of new physics. That decision would not be easy, and it would show again how visitors from beyond our solar system can test the limits of our theories. In this scientific sense, 3I Atlas is a probe whether or not it is artificial. We cannot launch a spacecraft today and wait millions of years to see how interstellar travel reshapes its structure and chemistry. Nature, however, has already done that experiment many times. When an object like this passes through our system, we have a brief opportunity to measure the outcome if our instruments and our thinking are sharp enough. While attention focuses on 3I Atlas close to home, other discoveries remind us that the same chemistry we see in comets also plays out on distant worlds. The James Webb Space Telescope, when it is not studying interstellar visitors, has been observing exoplanets, planets around other stars, and has delivered one especially interesting result this year. Using its infrared instruments, Webb has measured the atmosphere of a planet in the habitable zone of a nearby red dwarf star, roughly 40 light-years away. The world is somewhere between a large Earth and a small Neptune in size. By watching starlight filter through the planet's atmosphere during each transit, Webb's spectrographs can break the light into its component colors and look for missing wavelengths. Those missing pieces show where molecules in the atmosphere have absorbed light. In this case, the data reveal water vapor and carbon dioxide, which are expected, but also methane and more complex hydrocarbons in proportions that do not match the simplest chemical models. In an atmosphere shaped only by non-living processes, there are certain ratios of gases we expect based on temperature, pressure, and stellar radiation. Here, the measured methane to other hydrocarbons ratio is shifted in a way that could point to unusual chemistry, or, more cautiously, to processes that might include biology. No one is claiming proof of life. The signal can still be explained by complex but non-living chemistry in the planet's air, or by interactions between the atmosphere and the surface or interior. But the result is strong enough that follow-up observations are already planned. Scientists will look for additional gases and patterns that might help distinguish between geologic, prebiotic, and biological explanations. This connects back to 3I Atlas in 3 important ways. First, if a planetary system can sustain an atmosphere rich in complex organic molecules, it almost certainly forms comets and icy bodies that are also rich in organics. During the early stages of planet formation, outer regions of the disk collect volatile materials that eventually become comets. Some of those objects remain bound to their stars. Others are kicked out into interstellar space. A comet like 3I Atlas could easily be a fragment from such a system, carrying with it the chemical fingerprint of a distant world's outer regions. Second, the exoplanet result reinforces the idea that complex carbon chemistry is common. Given carbon, hydrogen, oxygen, and nitrogen, and enough time and energy, elaborate molecules tend to form. In 3I Atlas, cosmic rays acting on ices over immense timescales have produced an organic-rich crust. In exoplanet atmospheres, starlight and thermal energy shape mixtures of gases into unexpected combinations. Both cases tell us that the building blocks of life, though not life itself, arise naturally in many environments. Third, these threads together suggest that planetary systems may not be chemically isolated. Comets and asteroids can leave their birth systems and travel between stars. When they do, they bring with them samples of the chemistry that took place around their original star. If such objects are captured or collide with planets elsewhere, they can deliver that chemistry to new environments. In this view, the galaxy becomes a connected network of material exchange, with comets serving as slow messengers carrying the products of local chemistry across interstellar distances. 3I Atlas is one such messenger. The exoplanet atmosphere studies are another window onto the same, larger story. In both cases, our tools are limited. We infer composition and behavior from light alone, filtered through our models and assumptions. Often the data leave room for more than one interpretation. Yet by comparing many such cases, comets here, atmospheres there, we gradually build a picture in which organic chemistry is widespread, interstellar travel by small bodies is common, and the ingredients for life move through the Milky Way far more freely than we once imagined. For 3I Atlas, we see organic molecules, and for now, assume they formed through radiation, acting on simple ices. It is also possible that some fraction began as products of more complex chemistry in its birth system, maybe even chemistry linked to biology, and survived inside shielded pockets deep in the nucleus. We cannot show that is true, but we also cannot completely rule it out with the data we have. For the exoplanet, about 40 light-years away, we see unusual hydrocarbon ratios and consider whether life in its atmosphere might be shaping those gases. Yet it could just as well be uncommon but natural chemistry driven by the star's activity or by geological processes we do not yet understand. We cannot confirm life at that distance from a few spectral features. This shared uncertainty is important. It reminds us that cosmic observations rarely give a single, unambiguous answer. The universe is complex. Chemistry behaves differently under different pressures, temperatures, and radiation fields, and we are always working at a distance, with limited information filtered through our instruments and models. The fact that we can detect these signals at all is already a major step. Ambiguity does not mean failure. It means we have reached the edge of what our current tools can easily resolve. What makes this moment exciting is that we are now able to ask questions that were impossible a generation ago. We can detect organic molecules in the atmospheres of distant planets. We can analyze the chemistry of an interstellar comet passing through our own system. We can begin to see how the same basic physical laws and elemental ingredients play out in very different environments. 3I Atlas and that distant exoplanet are linked by shared processes: star and planet formation, ice chemistry, radiation processing, and the slow movement of material between regions of the galaxy. Together, they hint that the Milky Way is not a set of isolated systems, but a loose network where matter and information move gradually from star to star. While we are learning to read these faint chemical signatures, another development on Earth raises related questions about intelligence and interpretation. In late 2025, a major research lab reported that one of its artificial intelligence systems had carried out a complex scientific cycle with minimal human guidance. The system designed an experiment, analyzed the resulting data, proposed new hypotheses, and suggested follow-up work, all inside a loop that looked, in structure, like what a human research team might do, but at machine speed and scale. Supporters hailed this as progress toward autonomous scientific tools. Critics pointed to risks from systems whose internal reasoning we cannot fully track. Artificial intelligence has been present in science for years, helping to sift through huge data sets, identify patterns, and suggest new directions. The change here is not that an AI helped, but that it did so with more independence, deciding how to pursue goals inside a broad framework rather than waiting for detailed instructions at each step. That moves it slightly from pure tool towards something more like an agent, at least in practical terms. This matters when we talk about possible artificial probes from other civilizations. Real AI, the kind we actually build, does not resemble the conscious, emotional machines of fiction. It is more like an optimization engine, pattern recognition, and goal-directed behavior without any clear sign of inner experience. If a distant civilization sends probes between stars, the intelligence on board may well be some form of machine learning or algorithmic system designed to collect data, adapt to conditions, and make limited decisions, not a conscious mind in the way we normally use that word. That changes what we look for. Instead of expecting obvious messages, we look for behavior that suggests goals, trajectories that seem tuned rather than random, structured emissions, patterns in activity that reflect planning. In other words, we look for signs of autonomous problem solving. The same traits that make an Earth-built AI system interesting, its ability to pursue objectives and adapt without constant supervision, are exactly the traits one would want in an interstellar probe that must survive and function far from its creators. On Earth, we respond to growing AI autonomy by building safeguards, testing systems in controlled environments, monitoring their behavior, setting limits, and keeping the option to disable them if something goes wrong. With an object like 3i Atlas, if it were artificial, we would not have that luxury. We cannot sandbox an interstellar visitor. We can only observe it at a distance, try to infer its purpose, and decide how to respond. In that sense, our current debates about AI safety and governance are a rehearsal for a more challenging version of the same problem: understanding and living with intelligences whose internal workings are not like our own. Seen this way, the line between natural and artificial, biological and technological, becomes blurrier. If intelligence appears elsewhere in the cosmos, it may often be in machine form, systems built by biological creators, optimized for endurance and function rather than awareness. On Earth, we are now creating our own non-biological intelligences. Out there, similar processes may have been underway for much longer. Recognizing intelligence, in any form, becomes less about what it is made of and more about what it does. These reflections bring us back to a more local mystery: how well we understand our own solar system. You might think that after centuries of observation and decades of spacecraft missions, we would have a complete map of all major bodies orbiting our Sunday. Yet evidence continues to suggest that something large may be hiding far beyond Neptune. Statistical studies of the orbits of distant icy objects, sometimes called extreme trans-Neptunian objects, show a pattern. Several of these bodies have paths that are oddly aligned, as if their motions are being shepherded by an unseen mass. Analyses indicate that the chance of these orbital clusters arising purely by accident is small, perhaps less than 1%, though the exact number depends on assumptions about how objects are discovered. One widely discussed explanation is a planet with a mass somewhere between about 5 and 10 times that of Earth, orbiting the Sun at several hundred astronomical units. At that distance, such a planet would be very faint and slow-moving, difficult to spot even with large telescopes, but massive enough to gravitationally shape the outer solar system over long periods. Other explanations exist. Some researchers argue that the pattern might reflect observational bias. Our surveys do not cover the sky evenly, so we find more objects where we have looked more carefully, and that can create apparent clusters. Others suggest that instead of a single hidden planet, the combined gravity of many smaller bodies in a distant disk could produce similar effects. A few more speculative ideas involve a small black hole captured by the Sun long ago, or an interstellar object trapped in a huge elongated orbit. The link to 3i Atlas is not direct, but it is instructive. If there might still be a planet-sized body in our own system that we have not yet seen, our sense of completeness about the solar system is clearly limited. The outer regions of our cosmic neighborhood may contain more surprises, distant planets, captured comets, or objects that began as interstellar wanderers and settled into long orbits. In that context, an interstellar comet passing through is not an isolated curiosity, but part of a broader picture in which material routinely moves in and out of the Sun's domain. Searches for this hypothetical distant planet have intensified as new, more sensitive surveys come online. Wide-field telescopes scan regions of sky that were previously under-observed, looking for faint, slow-moving points of light. Whether or not a new planet is ultimately found, the effort underscores a theme that 3i Atlas also illustrates. Even close to home, our knowledge is partial. The solar system, the galaxy, and the universe still hold structures and patterns we have yet to uncover, and each new visitor or anomaly is another chance to refine or rethink the stories we tell about how everything fits together. In the coming years, the Vera Rubin Observatory is expected to begin full operations. It will scan the visible sky again and again, building a moving picture of anything that shifts position from night to night. That survey should be sensitive enough to either confirm a distant planet several times Earth's mass or place very strong limits on its existence. Until that happens, we live with hints, orbital patterns that strongly suggest something is out there, but not yet a direct detection we can point to. This uncertainty about the shape of our own solar system feeds directly into questions about interstellar objects. If we can plausibly miss a planet perhaps 10 times Earth's mass in our own backyard, what else are we not seeing? How many small interstellar bodies pass through the outer regions of the solar system too faint for our instruments? How many were captured long ago and now move on stable, distant orbits that we casually classify as native objects simply because they have been here for billions of years? The physics of capture is complex in detail, but simple in outline. An object on a hyperbolic path can, in principle, lose enough energy to become bound to the Sunday. That can happen through gravitational encounters with planets, through rare interactions that break an object into pieces with different speeds, or during the Sun's early life in a dense stellar cluster where close stellar passes were more common. These processes are all improbable on human timescales. Over the age of the solar system, they become almost inevitable. The outer regions may already hold many captured visitors, small and cold and far away, waiting in the dark. Seen in this context, 3i Atlas is one visitor we happened to catch because it passed close enough and became bright enough. For every such detection, there may be many more passages we never see, and many more captures hidden among the icy bodies beyond Neptune. Only detailed measurements of composition and isotopic ratios will tell us which objects truly formed with the Sun and which ones arrived from elsewhere. The deeper implication is that a solar system is not a sealed container. It is a region where a star's gravity dominates, but not so strongly that nothing can cross the boundary. Material comes in, either plunging through on fast trajectories like 3i Atlas, or settling into long orbits after rare capture events. Material also leaves, ejected by gravitational interactions into interstellar space, where it may eventually pass near another star and start the cycle again. Over millions and billions of years, this slow exchange mixes matter and chemistry across the galaxy. The search for a distant planet and the study of an interstellar comet are thus linked by a common theme. Both reveal how incomplete our map of the solar system still is. Both blur the line between ours and not ours. And both remind us that the region of space where Earth resides is not static, but part of a dynamic environment shaped by timescales far longer than human history. As December 19th approaches and we track 3i Atlas through its closest approach, it is worth remembering that beyond the reach of our brightest telescopes, other bodies, native and foreign, are also moving, contributing to the gravitational pattern that decides which comets dive inward and which remain forever in the deep cold. The sky is not empty. The solar system is not finished or fully mapped. Every new object we discover, whether clearly interstellar like 3i Atlas or only hinted at like a possible distant planet, adds another piece to the puzzle of how matter flows through space and time. From here, we can zoom out to the largest scales. All of these motions, all of these exchanges, take place inside a universe whose expansion is driven by something we barely understand: dark energy. Since the late 1990s, observations of distant supernovae have shown that the expansion of the universe is speeding up, not slowing down. To explain that, cosmologists include a smooth energy component that fills space and pushes it apart. In standard models, this dark energy is treated as constant in time and uniform in space, a fixed property of the vacuum. Some recent theoretical work, still highly speculative and not accepted as established science, has explored the idea that dark energy might not be perfectly constant. Analyses of the cosmic microwave background, the faint afterglow of the Big Bang, have looked for tiny temperature patterns that could hint at interactions beyond our current models. A few papers have claimed signs of slightly deeper cold regions than expected, or other subtle deviations, and have suggested that these might signal variations in dark energy or related physics. Most cosmologists treat these claims cautiously. The measurements are difficult, the differences are small, and alternative explanations, such as instrumental effects or statistical noise, are hard to completely exclude. The point here is not to argue that dark energy definitely changes, or that a particular cold patch on the sky has been proven real. The point is that even at the largest scales, the foundations of our models remain under active investigation. We work with theories that match many observations, but we also know that those theories may be incomplete. That same pattern appears at every level of our discussion, from comet activity and orbital dynamics to the behavior of space-time and the energy content of the cosmos. 3i Atlas has nothing direct to do with dark energy. A comet passing near the Sun is governed by gravity, outgassing, and radiation pressure. The accelerated expansion of the universe only matters on far larger scales, but conceptually, both topics teach the same lesson. Our confidence in our current understanding is always provisional. In cosmology, a new type of observation can force us to revise ideas about how space itself behaves. In planetary science, a new kind of object, an interstellar comet with unusual composition, can force us to revise ideas about how small bodies form and evolve. Interstellar travelers like 3i Atlas have moved through a universe that has been expanding throughout their journey. On human scales, the expansion is negligible. On the scale of millions of years and many light years, it is part of the background that shapes how distances and times relate. These objects are time capsules. They encode information about their birth environments, about the radiation they endured, and about the structure of interstellar space they crossed. When they pass through our system, we have a brief chance to read those records, if we are prepared. As we step back and look at everything we have considered, from disputed light curves and tiny trajectory anomalies, to questions about organic chemistry, possible biology, artificial probes, quantum gravity, dark energy, and hidden planets, a single thread runs through: uncertainty. The universe keeps placing us at the edge of what we know how to explain cleanly. December 19th may come and go with no visible surprise, only a set of new measurements and a better understanding of a natural comet. Or we may find something that does not fit, something that opens new questions instead of closing old ones. The most important readiness, in that sense, is not technical but mental. It is the willingness to accept that our models are tools, not final truths. It is the discipline to demand strong evidence for extraordinary claims, while still allowing ourselves to imagine possibilities and design tests that could confirm or refute them. It is the recognition that an interstellar visitor is not just an object in the sky, but a chance to learn about parts of reality we cannot reach in any other way. In the past century, our view of the cosmos has changed faster than at any time in human history. We discovered that the Milky Way is only one galaxy among many. We found planets orbiting other stars. We detected the first known interstellar objects passing through our system. Each step has shifted the boundary between here and out there. 3I Atlas is part of that ongoing shift. It reminds us that stellar systems share material, that the chemistry of the universe is interconnected, and that our solar system is only one small node in a much larger network. Whether December 19th becomes a date people remember or just another line in astronomy logs will depend on what we see and how we respond. The deeper message will be the same either way. The sky was never truly ours. It was always part of a vast, dynamic cosmos in which matter, energy, and perhaps even intelligence move on scales far beyond our everyday experience. Our task is not to claim ownership of that sky, but to understand it as clearly as we can, and to meet each new visitor from near or far with curiosity rather than fear.